right, let's look at the chapter 22 homework. So a food company sells salmon to various customers. The mean weight is 44 pounds, a standard deviation of 2. The company ships them to restaurants in boxes of 4, to grocery stores in cartons of 16, and to discount outlets in pallets of 64. To forecast costs, the shipment department needs to estimate the standard deviation of the mean weight of each type of shipment. So remember that what we're doing here with the standard deviation, we looked at this in the notes, right? We're looking at our standard deviation divided by the square root of the sample size, right? For it's the same mean, but the standard deviation is the standard deviation divided by the square root of n. All right, so if we have 44 pounds and a standard deviation of 2 pounds, then when I am doing 4 to a pack, right, boxes 4, I would be doing that standard deviation 4 divided by the square root, whoops, I messed that up already. It's amazing how quickly I can mess up. That's standard deviation of 2 divided by the square root of the number of fish, so 4. So this would be 2 divided by the square root of 2, so a standard deviation of 1. All right, now let's find the standard deviation of the cartons sold to grocery store. The cartons are 16. So I'm taking my standard deviation here, so the 2 and divided by the square root of 16, that would be 2 over 4, which is 1/2 or 0.5. So we're going to put in here 0.5. And then I'm looking at the 64. So we're doing our standard deviation that's given here, 2, divided by the square root of 64. That's 2 over 8, which is 1/4 or 0.25. Okay, so now the distribution of the salmon weights turns out to be skewed to the high end. Would the distribution of shipping weights be better characterized by a normal model for the boxes or the pallets? Okay, so the boxes only have 4 fish in there, but the pallets have 64. Remember, our cutoff is 30 to make for a normal distribution. So it should be the pallets, because as long as the underlying distribution is normal, the sampling distribution in the mean approaches to the normal model with sample size increases. There we go. Because of the, regardless of the underlying distribution. So it doesn't matter that it's skewed. As long as my sample size is big enough, the means will approach a normal distribution. We want to use T-table software or calculator to estimate. All right. We want to find the critical value of T for a 90% confidence interval. All right, so now if I've got a 90% confidence interval, that means looking at my normal curve, 0.9 is here, which means the remainder, 1 minus 0.9, would be 0.1, and that's split between here and here. So this would be half of 0.1, which is 0.05, and this would be half of 0.1, which is 0.05. Okay, so I'm going to pull out my calculator. So I want to find the critical value for 90% off confidence interval. So we're going to go second distribution. My inverse T is option 4. The area is the 0.05. And my degrees of freedom, it says right here, are 20. Right? paste that, and we get 1 point. No, this is the negative one, and then by symmetry, the positive one is over there, right? So it's plus or minus. So remember, we just drop the sign, keep the number for a critical value, 1.725. Or how about 1.72 if we round to 2 decimal places? All right, now we're doing a 95% confidence interval with 61 degrees of freedom. Well, if it's 95, then that means here is 0.95. So half of the remainder, which is 0.05, is here. So 0.025, half of the 0.5 on each side. So if I do same key command, but we're changing this to 0.025. And the degrees of freedom to 61. That rounds to 2, right? To 2 decimal places, that would round to 2. All right, the p-value for t greater than equal to 1.52 with 7 degrees of freedom. All right, so we're going to use second distribution, and there's our TCDF right there, the cumulative density function for the t curve. Just like we were using the normal CDF for the z's, we use TCDF. So I'm going to choose option 6. I'm going greater than or equal to 1.52. So let's go 1.52 is the lower. The upper is going to be a really big number. And my degrees of freedom are 7. And so it's 0.086. And now the p-value for t greater than 1.93 with 20 degrees of freedom. So we're going to do the same thing, but it's 20 degrees of freedom. And we want to go bigger than 1.93. Now, notice I get 0.3 whatever. All right, now take a look at what's going on here. So my t of 1.52, I was bigger than or equal to, so I got my t value here bigger than or equal to is that way. So this is the same thing, but it's not equal to, doesn't matter because that's just a single point, but it's an absolute value. So that means if this is the 1.93, over here at the negative 1.93, I'd also want this area over here, but all the calculator found is this area. So I'm going to times by 2 to get the other symmetric area. 0.068. All right, so now I want to describe how the critical value of t for a 95% confidence interval changes as the number of degrees of freedom increases. So remember what happens on the normal curve here. My t curve is wider and flatter. But as the degrees of freedom increase, it becomes narrower on the ends and taller and higher, more like a Z curve in the middle, right? So as the degrees of freedom go up, it becomes more and more like a normal Z curve, right? All right, so we want to say, as the number of degrees of freedom increases, the critical value of T increases and approaches the critical value of Z. Okay, it doesn't, oh, then the critical value of T Wait, so for a 95% confidence interval, okay, let me show you the curve here. There we go. So there's our t distribution. So now notice if 95's in here, right? My t value would be backing up towards the normal curve as it gets higher. That means that critical value would be decreasing. Okay, and then for a 95% confidence interval, the z should be 1.96, not 1.645. So it should be answer C here. Okay. Software analysis of the salaries of a random sample of 275 teachers in a particular state produce the confidence interval shown below. Determine if the following conclusions are correct. If not, states what's wrong. If many random samples of 275 teachers from this state were taken, about 9 out of 10 of them would produce this confidence interval. No. About 9 out of 10 intervals will contain the true mean salary, but different samples of 275 teachers will produce different confidence intervals. That's true. Every time I do this, I'm not going to necessarily end up with the same confidence interval, but most of them, 9 out of 10, if I'm 90% confident, most of them will contain what the true mean salary is. If many random samples of teachers from the state were taken, about 9 out of 10 of them would produce confidence interval that contain the mean salary of all teachers from this state. If many random samples of teachers from this state were taken, about 9 out of 10 of them would produce a confidence interval that contained the mean salary of all teachers from this state. That sounds true. So the conclusion is correct, assuming all assumptions and conditions are met. About 9 out of 10 teachers from this state earn the, no, it's not on the teachers from this state. The 9 out of 10 is how many of the confidence intervals will contain the true mean salary. There we go. Oh, not the sample mean, it's the population mean. I didn't catch that. Population mean salary, not the individual teachers. About 9 out of the 10 teachers surveyed earned between those amounts. Nope. Not the salary for individual teachers. Same answer. We are 90% confident that the average teacher salary in the entire country, no, it's for this state. A researcher measured the body temperatures of a randomly selected group of adults. The summary of the data collected are in the accompanying tables. Estimate the average or normal temperature among the adult population. Okay, so here are summary statistics right here. Okay. So we've got 52 People participating, this is the mean and our standard deviation. Okay. So, randomly selected. Temperature is normally distributed, and 52 is less than 10% of all people, so all conditions should be met. Find a 95% confidence interval for the mean body temperature. All right, so our mean confidence, our confidence interval is our formula right here, right? So I need the T critical that goes with this. So we had 52 people. So our degrees of freedom is 51. And it's a 95% confidence interval. So remember the picture. That means 0.95 in the middle. We want to know the T critical, right? That's the negative and that's the positive of it. So I'm going to do second distribution, inverse T, and then half of the remainder. So the remainder is 0.05. Half of that would be 0.025. My degrees of freedom were 51. So that is negative 2.008. My T critical is 2.008. Okay, so now looking at my formula, I want to do the mean plus or minus that T critical times the standard error. So that mean is 98.691. Minus my T critical is 2.008 times the standard error. So my standard deviation, 0.6791, divided by the square root of the sample size, 52. That's my standard error. Oops. Okay, there's my lower bound, and then let's do it again and change that to a plus to get the upper bound. Okay, so we want to go, this is 2 decimal places. 98.50 to 98.88. Explain the meaning of the interval. There's 95% confidence based on the data that the mean body temperature for an adult falls in the interval. Nope. There's 95% confidence based on the data that the interval contains the mean body temperature. Sounds about right. Mean body temperature walls fall in the. So that's containing the true mean. Explain what 95% confidence means. 95% of all such random samples will produce intervals containing the true mean temperature. A temperature of 98.6 is commonly assumed to be normal. Do we agree with that? Well, no, we think it should be between 98.5 and 98.8. So yes, that's in that interval. What are the chances your flight will leave on time? To the right of the histogram and summary statistics for the percentage of flights departing on time each month from 2001 through 2006. There is no evidence of a trend over time. Independence is met because, right, these are flights that are departing on time for these years. There's no reason to believe that they are dependent on one another in any way. Randomization. It does not say that the randomization condition is met, but there's no reason not to believe that these aren't representative of all flights, right? So I'm actually not sure whether they want me to mark yes or no there. I'll say yes, and you may change it to a no. Okay. And the 10%. So certainly these would be, 72 would be less than 10% of all flights. Nearly normal. That almost looks like a bell-shaped curve in that histogram, so sure. 90% confidence interval. Okay. So, and actually, I think I did this last time using the formula, but if we go to stat, tests, and T interval right there, option 8. Let's input our mean, which is 80.6528. And the standard deviation, which is 2.42. 074. And the N is 72. And our confidence level is 90%. So there we go. 80.177. 2 decimal places. To 81.13. Choose the correct answer. Okay, so there's a 90% chance that the true mean, you can be 90% confident that the interval contains the true mean. A researcher tests whether the mean cholesterol level among those who eat frozen pizza exceeds the value considered to indicate a health risk. She gets a p-value of 0.16. Let's explain what that means. If in fact the mean cholesterol of pizza eaters does not indicate a health risk, then only 16 of every 100 samples would have mean cholesterol levels as high or higher as observed in this sample. That sounds right. No, this says nothing about people eating frozen pizza. This indicates health risk. That's wrong. Right? Oh, okay. That's okay. So it's based on the sample that we took. 16 of every 100 samples would have a mean cholesterol level as high or higher than what we observed. That's always the meaning of the p-value that you're looking for. Okay. Congress regulates corporate fuel economy and sets an annual gas mileage for cars. A company with a large fleet of cars hopes to meet the goal of 35.4 miles per gallon or better. If the goal is being met, they check the gasoline usage for 37 trips chosen at random, finding a mean of 37.4 and a standard deviation 3.74. Is this strong evidence they have attained their fuel economy goal? All right, so we want this or better. So our null is that we equal 35.4, and better would be that we're larger than 35.4. Are the necessary conditions made? The company uses a random sample. Yep, chosen at random. Company uses random samples, so one can assume the data are independent. If the sample size is less than 10% of the population, and certainly 37 probably is, and there are at least 10 successes and 10 failures, no, that's for a proportion. If there are no outliers and the data are unimodal, symmetric, and only mildly skewed, one can assume the data comes from a normal population. Describe the sampling distribution model. All right. Okay, our mean was 37.4. So it should be here we go. Our mean minus 35.4 divided by our standard deviation divided by the square root of the sample size. This is the null hypothesis value. So, and it's approximately equal to a t distribution with 36 degrees of freedom, one less than the number in the cars. Find our p-value. Okay, so let's run the test. Stat, tests, t-test. Our mean is 35.4. Our sample mean is 37.4. Our sample standard deviation is 3.74. And our n is 37. Our hypothesis was bigger than the mean. So our p-value is this 0.001. The probability of observing a sample mean higher than 35.4, no. If the average fuel economy 35.4, the chance of obtaining a sample mean of 37.4 or more by natural sampling variation is the 0.1%. So we should reject the null hypothesis because that value is less than 0.05. There's strong evidence that we're meeting our goal. Students investigating the packing of potato chips purchased 6 bags of chips marked with a net weight of 29.4 grams. They carefully weighed the contents of each bag according to following weights. Yeah. So randomization may not be satisfied, but these bags are representative of all bags of chips. They didn't show me a histogram. But I'm gonna bet that's probably true. So let's see. We're gonna go to stat, edit. Let's clear our lists and enter these values into list 1, 29.2. 29.1. 28.6. 28.5. 28.7. And we'll go into the y equal, turn our plots on, and we want to make a histogram from list 1. Good. Now go to zoom, stats. It's a little bit skewed looking, it kind of. I don't know if I'd classify that as unimodal and symmetric. Let's see. So if we imagine like a histogram coming over that, there would be a little bit of skewness there. I don't know that I would feel comfortable saying this. Our scale here is 0.2. Let's change that. It doesn't work. Get a little bit better picture. That makes it look uniform. Yeah, so this is not very normal looking data, to be honest with you. So I'm kind of tempted to say not symmetric. It's kind of binomial. So let's try it and see. No, it is going to say it's roughly unimodal and symmetric. I'm not sure I agree with that entirely. I would want more data in here to really classify that as kind of unimodal and symmetric. That's not really roughly symmetric. That's a very rough symmetry. All right, let's find the mean and standard deviation. So we're going to go to stat, calc, 1 variable statistics on L1. Our mean is 28.75. And our standard deviation is 0.3233. %95% confidence interval, stat, tests, T interval. This time we have the data, list 1, and we wanted a 95%. 1 decimal place. Explain what it means. We are 95% confident that the interval contains the true mean. Natalie ran an experiment to test optimum power and time settings for microwave popcorn. For Her goal was to deliver popcorn with fewer than 13% of the kernels left unpopped on average. She determined that power 9 at 4 minutes was the best combination. She concluded that this popping method achieved the goal of fewer than 13% of kernels left unpopped. It really does not work that well. Okay. So she concluded it worked when it really did not. That should be a type 1 here. To be sure that the method was successful, she popped 8 more bags of corn. All right, so we're testing these 8 bags. So let's put them in our list. All right, so we're going to go stat. By the way, we would check all of the conditions and make sure we can run our t-test here. The mean was 13%. All right, she wanted fewer than, so that should be less than. All right. So our null hypothesis is it equals 13. Our alternative is less than 13. Our t statistic is that -3.089. Our p-value 0.0088. So that's less than the 0.05. So yes, there's enough evidence to reject the hypothesis that 13% or more of the kernels were left unpopped. A company announced a 1,000 chips trial claiming that every 18-ounce bag of its cookies contained at least 1,000 chocolate chips. Student purchased random bags of cookies from different stores and counted the number of chips in each bag. Some of the data is shown below. Random. Histogram. All right, so we're going from, well, here's 1497, so I know it's not this one. So if this is 900,000, 1,100, 1,200, 13, 14, 15, and then 1,600. Okay. So this is between 1,000 and 1,100. 1, 2, 3. Should have 3 values there. between 1,000 and 1,100. 1. Oh, that's not one. That's not one. Should only have one value there. So this is the histogram. And by the way, I could have plugged those numbers into my calculator and drawn the histogram. That's roughly unimetal and symmetric, no outliers, so normal model. Okay, I need to put them in here now. All right, so 1,004, 1247. 1171, 1248, 1131, 1382, 1300, 1310, 1233, and 1497. Now, by the way, to do the histogram, you just go stat, make sure it's on, histogram is checked, then go to zoom 9. There's what my histogram looks like when you were matching it up. That doesn't look anything like it. We would have to change the scale. So go to window. We want it to match the X scale to be 1,000, I think it was. No, I'm sorry, try what again, 100. There we go. And now we can see the matchup. That ours looks absolutely nothing like theirs. But that's because, why is that? It should. Our scale's just a little different. But you can still see that it's roughly the unimodal and symmetric. All right, now 95% confidence interval, stat, tests, 8. Input the data, list 1, we wanted 95, we're good. Whoops. Try that again. Okay, 1155.2. To 1349.4. All right, so their claim was that it contained 1,000 chips. This is true. What? Oh. Yeah, I'm sorry. I should have gone with this. Right. It's about, remember that a normal model, you know, you've got a normal distribution, some above and below. Students investigated the packaging of potato chips. All right, now let's double check that really quickly by entering this data. All right, so 29.4, 28.3, 29.2, 28.7, 28.8, 28.6. And if we go to our stat plot, we're on zoom 9. Okay, yeah, you know, I mean, that's very roughly unimodal and symmetric, but it is. So our nearly normal condition is plausibly satisfied. We're good. All right, our mean weight. So the mean weight is 28.83. Standard deviation is 0.40. Our null hypothesis is that we equal 28.3, and the alternative, notice it says they're investigating. It doesn't say whether they think it's above or below. So we're going to go with it does not equal, a two-sided. And our test statistic is the 96.16. What? Okay, did I enter something wrong? Let's look at it. No, I got the right mean and the right standard deviation. Did I put in the wrong hypothesis value? Let's double check. Yes, I'm such an idiot. I left the null as 13. Should have been 28.3, the company's claim, right? Oopsie. All right, 3.24. P-value is the 0.023. State your conclusion. Notice that this is less than the alpha value, so we are going to reject the null. There is sufficient evidence that the mean weight is different from what our alternative hypothesis is. T distributions have fatter tails and narrower centers. T distributions are symmetric and unimodal, that's true. As the degrees of freedom increase, T distribution approaches the normal distribution. They do have fatter tails. Narrower centers. I'm not sure what they mean by narrower centers. Well, let's say that's true, right? Because I guess by narrow, they mean like that flatter middle. It's not as sharp of a curve. Narrow there's weird. Suppose we are making a 95% confidence interval for the population mean from a sample of size 15. What number of degrees of freedom should we use? One less, 14. Suppose I want to test whether students' textbooks costs for the semester are higher on average than the costs of $450. What would be an appropriate hypothesis? Higher than would be bigger. A student on the track team wants to test whether her times to run a mile are different. So a does not equal would be different from 8. Suppose we construct a 90% confidence interval for a mean. This is equivalent to a two-tailed. Oh, okay. So let me go ahead and show you what I mean here. So remember that you have 95%, whoops, in the middle on this, which is 0.95 here. Oh, 90%, sorry, 90 in the middle. And so that means 0.1 is split on the outsides, right? So a 90% confidence interval would be equivalent to a two-tailed hypothesis test with our significance level right? We're looking at 0.05 over here and 0.05 over here, splitting the 10% left over. So 10% split of the two, 0.5. All right. So this is your homework for chapter 22. If you have any questions, be sure to let me know.